Today we're modeling with composed functions. This is the day where you really get to see, like, what's the point in all of this. Take a look at example 1. At first glance, to me, this feels kind of overwhelming. So let's break down some of the pieces that we know. Okay, so it says the hot air balloon rises on average 100 feet per minute. Okay, so we could say that the height of the function in terms of the number of minutes that have passed, notice I'm writing equations out in words so I can help myself sort of make sense of what's going on. It rises 100 feet per minute, so maybe I'm thinking, okay, I don't really know what the relationship is here. At 0 minutes, it probably hasn't gone anywhere. After a minute, it goes up 100. After another minute, it goes up another 100. After another minute, it goes, oh, this is just 100 times m. Okay, so that's that fact. Let's see, at sea level, the atmospheric pressure is 29.9 inches of mercury. Hg is on the periodic table, it's mercury, which is like a really thick liquid. And so to measure pressure, you would use sort of like a thermometer. Back in the day, they would actually have mercury in it. Now it's pretty unsafe. But you would measure the height, the number of inches of this liquid mercury as a measure of what the air pressure is. Okay, but that fact didn't really tell me anything. I'm not sure yet how to use that fact. That's okay, we'll come back to it. Using a barometric meter, which again would be something like this. It would look sort of like a thermometer. Bob notices that the pressure decreases by 0.5 inches of mercury for each 500 feet the balloon rises. Okay, let's see what's going on here. The pressure seems to be a function of the height. Okay, so I've got pressure in terms of the height of the balloon. I don't know what this is saying, so let's make a table of values and see if we can sort out this relationship. It's saying whatever the pressure is here, if we go up 500 feet, whatever this original pressure was, it'll go down by 0.5. Then we go up another 500 feet, it'll go down another 0.5. And then we go up another 500 feet, the pressure will decrease another 0.5 inches of mercury. Okay, so this pressure, it's going down, right? Multiples of negative 0.5 per every 500 feet. Let's maybe just double check a couple values to make sure this makes sense. If we substitute in 0, we've got negative 0.5 over 500 times 0. Okay, well, that makes sense. You have some initial value. And if you substitute in, let's say, 1,000, then we have negative 0.5 over 500 times 1,000, which reduces to 2. Well, that makes sense because this is 2 increments of 500. So you would decrease 2 times negative 0.5 inches of mercury. Okay, well, let's keep reading. What is the reading 10 minutes after? So what's the reading on the barometer? What is the pressure after 10 minutes? So I would like to say the pressure after 10 minutes is some number of inches of mercury. Okay, well, the pressure we know depends on height, and height depends on minutes. Okay, well, let's write out pressure in words. The pressure of, in terms of the height, maybe this is where we can use that fact at sea level. Sea level is a height. It's the height of 0 meters above the ground or 0 feet above the ground, right? So the pressure in terms of height would have to be some initial pressure minus, what are the other things that have to do with pressure? Oh, height, right? And so it would be minus the decrease in pressure as you climb or as the hot air balloon rises. So the initial pressure at sea level is 29.9 inches of mercury. And we know that it's decreasing every 500 feet that you rise the pressure decreases 0.5 inches of mercury. So we can multiply this, right, the decrease of negative 0.5 per 500 feet by the height measured in feet. Okay, well now we have this function P of H, but what we really want is P of M. We want to be able to substitute in 10 minutes. Oh, well, how nice is this? We already have a function H in terms of M. So let's substitute that function in here. The pressure in terms of minutes, well, we're going to have to substitute H of M. It's going to be 29.9 minus 0.5 over 500. Instead of just writing H, we can put 100 M. Because we know the height in terms of minutes is 100 times the number of minutes. And so now we have a function P in terms of M. So now we can substitute. What we wanted was what's the pressure after 10 minutes? Well, the pressure is going to be 29.9, that pressure at sea level, or the initial pressure, minus 0.5 over 500 times 100 times 10. This is super messy, but whatever. Just throw it into your calculator. And what you're going to get is 28.9 inches of mercury. This is the point of function composition. A lot of variables are related, right? We're relating height to minutes and pressure to height, and we've got an initial pressure. It can just be, honestly, sort of hard to sort out all the information. But if we break down the functions into individual pieces by just looking at one relationship at a time, height to minutes, pressure to height, that helps us see the big picture by putting together the functions through substitution, through composition. Okay, one more example today. A consumer advocacy company does this study, okay? It makes sense that the price of the orange is going to depend on how much it weighs, and how much it weighs is going to depend on how big it is, right? Its size, which you can measure in radius or diameter or whatever. Use the table to evaluate P of W of 2 and interpret this value in context. Well, this is similar to what we've done before. First, we're going to take a look at W of 2. That would be the weight of, well, let's see. If weight is my Y value, weight is in terms of the radius. So this 2 must be a radius value. So what we want is P of 0.5. Well, if P is my Y value, what I'm substituting in is a weight, right? This output, the Y value W, became an input. So P of 0.5 is 0.65. And so what that tells us is that my original input R, if R is 2, then my output P is 0.65. That's like saying an orange of radius 2, 2 inches will cost $0.65, right, or 65 cents. This allows us to skip the middleman. We don't actually care how much the orange weighs. I just want to know how much it's going to cost, right? So I can directly relate the original input to the ultimate output. An orange of radius 2 inches will cost 65 cents.